We often hear about different factors that drive an additive business case. And although the consensus is that additive can bring great business value, there are a varying degree of opinions on the type and depth of value that can be achieved. In order to determine possibilities to add business value through additive manufacturing, it is essential to be aware of some of the basic underlying principles. What do you think is the most important consideration when building an additive business case, and why? Hi, everyone, and thanks for joining us for another edition of Webinar Wednesday from GE Additive. For those of you who have joined us for previous webinars, welcome back. And for those of you who are joining us for the first time, welcome. I'm Allison, and I'm the moderator for today's webinar. Today's webinar topic, Understanding AM Economics, a critical piece of additive business case. I'm joined today by my colleague, Nick Szabo, who is one of our technical commercial consultants. Nick began his work with GE a decade ago, joining the GE Aviation team, focused in advanced component design using all manufacturing methods. He joined the Tiger team dedicated to identifying AM applications in 2013 and eventually joined GE Additive in 2016, helping to launch our engineering consulting business. Nick holds a Bachelor of Science in Engineering Management and a Master of Business Administration from Miami University. After spending several weeks reviewing the content for today's webinar with Nick, I am certain that you'll find this hour insightful, with several key takeaways to be learned. So before we get started, I'll go over a few quick housekeeping items to make this a more enjoyable experience for you. At the bottom of your screen, you'll find multiple engagement tools which you can use. And all of these engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You also have the option to expand the slides or maximize them to full screen by clicking the arrows in the top right corner. I'll also ask that you please complete a short survey that will pop up for you at the end of the webinar to share with us how your experience was today, and let us know any other topic you'd like to hear about in the future. We do have materials that are available for you in the resource list, and I encourage you to download any resources that you may find useful. If you have any questions for Nick during today's webinar, please feel free to submit them using the Q&A section, which is located on the right-hand side of your screen. We'll try to answer as many questions as we can at the end of the webinar. Now that we've gone through how to make the most of the viewing experience, let's get to today's webinar.
All right, thank you, Allison. So I'll cover the agenda for today's topic. By and large, we're going to be talking about how do we establish common language used to kind of talk about machine productivity, the machine itself. We'll discuss some of the common myths about additive manufacturing, stuff that you'll hear, maybe that you've heard over the last several years. And we'll ultimately show some examples of how to accurately predict some of the AM costs and productivity. So we'll start kind of with a high-level view of the entire discussion. So at the end of the day, everybody's here because they want to understand how to create a viable business case using additive manufacturing. So a business case really can be defined as the justification for making any type of investment and ultimately what the commercial consequences are. Is it profitable? Does it open up market space? Does it create opportunities that you otherwise didn't have in your current business arrangement? Those business cases are the thing that we really focus a lot of our attention on, but they're really constructed of sort of 3 to 4 major components. And so ultimately you can see here at the root of it, the core of building a successful business case really comes down to your cost estimation and coming up with a very accurate predictive model for cost of additive has been the subject of a lot of discussion and debate for at least the last 5 years, if not much longer than that. So we start at the core. The cost model really is a sort of simple accounting exercise where we take into consideration what the machine is actually doing. So this is kind of the open secret about additive manufacturing, and this is going to be true for a lot of things outside of additive, that the machine behavior is one of the things that really dictates how to estimate your cost. So in this case, when we're talking about machine behavior, we're really talking about what is the machine actually doing, because that is important. Similar to human economics, we focus on behaviors, consumer behavior. In the case of machine economics, we talk about what the machine is doing. And so that's one of the major takeaways of today, and we'll dig much deeper into that as we go. So let's say that we have a cost model that we actually, we believe in the results, it's been verified, and we, have a very complete, comprehensive model. The next thing that we really want to take into consideration are the performance factors. So ultimately, this can be things like I'm producing a brand new product. I have new capabilities in that product. So that would be, in the case of a derivative, sometimes you can have derivative savings as a change in a product happens. So something in aerospace that we commonly see, for example, is weight. There's a premium that's paid for weight, and if there's a way to optimize on that, you can actually derive substantial direct cost savings. But another common thing that we do with additive is we actually increase the life of components. And so that increased life has, a lot of consequences on what your downstream manufacturing maintenance costs are, and it has a lot to do with, changes in, potentially getting into changes in your own supply chain if you're able to increase the performance of the part and the life of the part. Naturally, that segues into a much deeper discussion about supply chain disruption. So in the case of additive supply chain, in a lot of ways, you're really disrupting the necessity to go out and actually get tooling made, dies, molds for castings, for example. And so in a lot of ways, you start eliminating a lot of the intermediary requirements from the supply chain. You no longer have to go out and source those people, get them, potentially months in advance, and have them lined up to actually perform the work that you want to do, especially when we're talking about development. So another thought here is that with additive, if you do bring it in and decide to vertically integrate, now that you're bringing that manufacturing in-house, maybe you can drastically reduce the scope and scale of your existing supply chain in terms of human resources and capacity. In some cases, this will be a reduction of warehouse and storing. Sometimes, you've probably read several articles about this, you can actually reduce the amount of obsolescence that's happening to a product line. You don't have to obsolete products just because you have a tooling piece, a mold, something like that the supplier went out of business 20 years ago, and you're scrambling to try to find somebody who can replace that component. So additive really can come in and really work wonders when it comes to the supply chains for an existing business. But lastly, I think one of the big things that we want to talk about is the overarching business case. Why would we even go additive in the first place? So it's one thing to say, well, I can estimate my costs pretty well. I can understand the performance changes that I've made to my parts by going additive. I can even talk about the substantiation of my supply chain and the changes that are made there. But ultimately, the business case hinges on what you can do different from the highest possible level. So in this case, maybe additive technology is going to be something that puts you into an entirely new marketplace. And in some cases, you can actually construct different business models that might be fundamentally different from what you're doing today. In a lot of ways, it'll offer better differentiation, and that's kind of a minimum entitlement. And if you've really leveraged additive, you're not just taking a casted part and deciding to print it, even though sometimes that is exactly what you want to do. In many cases, to really get that immediate benefit, you start from the design and work your way up. So by creating that product differentiation, does that make you more competitive? Does it take you from competing in a red ocean? Getting more into a blue ocean, you're paving the way for new industries rather than simply competing in your current market space. So ultimately, there is a way to lower expenses, and this is one of those maybe topics that's hard to kind of wrap your head around, because obviously additive, because it's a new technology, it's an emerging technology. There's a lot of costs associated to kind of breaking into it. But if you really structure your business and your supply chain around that, it actually has the ability to definitely lower how much money you're actually spending on a recurring basis from overhead expenses, a reduction in new product development in RE as well. But, in some ways it can actually lower the human resources expenses as well and reduce that as a variable cost. So we'll talk about some of the additive machine metrics that you might want to keep in the back of your head throughout this presentation, but ultimately this is something that you'll probably want to think about as you start building out your business cases. So the first one is build time. You'll hear a lot more about the influence of build time on your cost predictions later today, but we kind of want to set the stage and say that there's a summary of all of these different events that are happening at the machine that contribute to your overall build time. So it really is the summary of all of the different scan times that happen on the machine, and that's another deep topic that we could probably cover in another hour. But when it comes to all the different ways that the machine actually behaves, we have to sum all of those together. We have to characterize them, sum them together. But we also have to do the same thing with the way that the powder or filament or anything that's being fed into the process is being processed. So in the example of DMLM, that could be something like the time it takes to actually recoat each layer, deposit a new fresh layer of powder before you begin the scans. And ultimately, there are pauses in the process. That's something that a lot of machine OEMs are working to eliminate, but sometimes you can't. And sometimes having an induced pause actually results in better part quality. There's a lot of things happening from a thermal perspective, layer by layer. So the process, because it is a melting and solidification process, there is a transient which requires some time. So sometimes you want to use the pauses to your advantage, but you do certainly have to account for them in the build time. So the other major thing, and this is something I feel is a broad-reaching industry metric. This is very common in automotive. This is also going to be very common in other high-throughput scenarios, maybe like a consumer products type industry. But overall equipment effectiveness. So the way that we kind of refer to it, and you'll see me using these words a little bit interchangeably today, but it's really about availability of the actual machine. How much time do I have available to make the product? And that, in our mind, is considered utilization. So when we talk about performance, it's really the throughput, or how fast, how productive is the process. That is a subject that we're going to cover in much depth throughout today. And then ultimately, quality. Another way of thinking about it is yield. So how many useful parts am I actually getting out of the process? So even if you had something that was highly productive and was available 24/7, if you had poor quality, that could have a really tremendous impact on the amount of cost that you have to incur, essentially printing parts that wouldn't be usable. So all three of these aspects are really the primary focus of machine OEMs today, using today's state-of-the-art technology. We really want to make sure that the machine is available as much as possible, that it has the maximum amount of throughput while keeping quality at whatever your quality requirements are. And so that'll be, some of the levers that you get to pull is that, can you trade quality for performance? Can you trade performance for availability? As you start to work through this equation from a high level, that's the kind of stuff that you'll want to actually think about and make the trade and present ultimately in your business case. So we'll take a break here, and I'll pass it over to Allison for a question.
Great, thanks, Dick. So our first poll question today, it's an easy one for you guys. Complexity is free. Something we hear quite often in this industry is this statement. So do you believe that complexity is free? True or false? I'll wait a couple more seconds, give everyone a chance to fill out the poll. And we'll go ahead and take a look at the results from today. So 28% believe that yes, complexity is free, and 73% believe that false, complexity is not free. So Nick, what do you think about the results of the poll today?
Well, I think we've got a smart audience. So I think this is actually, exactly what I was expecting to see. And I think the reality is for advanced users, I think we're aware complexity has a cost associated to it. And I think for those who answer true, I'll walk you through why sometimes it's not true. So if we really think about it, additive manufacturing can enable more complex geometry. I mean, in fact, just point blank, you can print things that you can't make any other way. And that in itself is a super powerful thing. And it's something that if you leverage it right, that is the thing that pushes you into a winning business case. But one of the major things to really think about is that the cost of complexity with additive manufacturing does go up as the part becomes more complex. And so even though it may, absolutely be much more competitive than a traditional process, complexity does contribute to the final part cost when it comes to additive manufacturing. And so we'll kind of walk through some examples here. So to try to explain why complexity contributes to the part cost, all additive machines, and this is going to be true for every process, and it's true beyond additive as well. Most machines are really just a set architecture, and then they receive a set of instructions on what to do from for example, a G code or some other type of method where you're inputting the instructions in the machine. So in this case, we'll refer to them moving forward as themes or parameter sets. You'll hear that commonly if you've ever worked with GE Additive in the past. But those parameter sets and those themes are the thing that really determines how long the machine actually operates. So there's also another side of this, that what the contents are of those parameter sets, they derive all of their instructions from the CAD model. So it's kind of a two-step process where I have to define the geometric complexity in the model itself, generate the CAD file. Whenever I load that into whatever subsequent software I'm using to perform my slicing, that slicing is the act of converting the information in the CAD, converting that over to a set of instructions that the machine can interpret and then decide, what type of exposure or, what type of laser power, speed, et cetera, I want to actually use to deposit it. So with this is a lot like painting with a bunch of different brushes. So if you're painting, a large room without any, fine details, a roller brush is going to get the job done a lot faster. And so we have the ability to sort of have a roller brush type exposure happening in the machines, which enables a lot of material to be deposited pretty quickly. So kind of the opposite of that is that if you've ever tried painting something that's really intricate, detailed, getting into like maybe you're actually painting a photograph rather than just a wall in a room. If you're taking the time to, pay attention to the different color, the different lines, the different blends, all of a sudden we have something that's much more complex. And that's exactly what's happening on the machine level. So we get to a set of instructions that's actually like having a bunch of different brushes available to you at all times. And which brush you use really depends on the geometric complexity of the part. So if you think about it from just a pure kind of visual perspective, the part complexity determines the exposure element assignment for each layer. So in the case of like a DMLM process, this will be true for really any powder bed type process. The complexity, the geometric complexity per layer is actually the thing that's driving, the amount of time it takes to process. So we have these two examples here. We have a green object that's on the left-hand side. This is a much more complex geometry. So you would know this kind of intuitively. You look at it, it's kind of a bulk in the middle, and then it has a bunch of little tiny, maybe a compound radius curvature to it. And on the right, we have this red, simple, almost donut shape. The people with great eyes are going to see there's a couple little notches up in the top, but that level of complexity is by far simpler than what we're going to see on the left-hand side. So if you look at just the raw numbers, 32 seconds to generate this complex geometry on a layer basis versus 23 seconds for the simple geometry. So, in the grand scheme of things, 10 seconds, does that really add up? Well, if you have thousands of layers and you're running multiple machines across an entire year where you have a lot of availability, that adds up very quickly. And that can be one of the contributing costs. So, sometimes it's a little bit of a trade with additive technology. Do we go with something that's really complex? And do we get our derivative savings, for example? If we go with something that's more complex, maybe it performs better. Maybe it's much lighter and I know exactly how to do that cost trade. But adding complexity just for the sake of using something complex that looks quote unquote additive, it may not be in your best interest. And in some cases, it's actually better to simplify a geometry in order to converge on a winning business case. So if we think about how complexity is really driving build time, so there's at least two major geometric considerations. And this is something that you can, work on at the CAD level, but it's also something that you can kind of take with you throughout the entire process. But really, if you think about it, more surface area means that I'm exposing more of these contour shapes. Or, in other words, the more surface area there is, the more I have to pass a laser around the edge of the part. And there's a reason why we do that, and we'll talk about that on the next slide. But if we are talking about, really bulky geometry, that's really associated to the volume of the part. And so one kind of nice objective way to measure complexity is actually just a ratio of these two things. So if you want to define complexity, this is a great place to start because you're going to capture how much of the process is biased toward my, fine detail, edge passes, high resolution type brush, if you will, whereas how much of that is assigned to the roller style brush. So how much faster can I deposit my material? So this is something to really take into consideration. What we're looking at here is just a simple example of a standard slice. And you can kind of see there's a lot of red, type of hatch that's in the middle of these parts. So that's all of the hatch exposure. That's the specific instructions telling the machine to, put the roller over these areas. But we also have the outlines in the blue are the contour exposures. And so it may not be intuitive, looking at it, but there's actually much more surface area. And there's much more contour in the part on the right-hand side. And so that's just two exposure elements. So we've talked about the hatch and contour. There are actually up to 24 other exposure elements that happen, different associated to different geometry implications, and in some cases, not just the geometry itself, but the interpretation of that geometry. So now we're talking about part nesting, and we're talking about part orientation that's contributing to how complex the geometry is on the slice level. So this is kind of an interesting spot because now we're saying, there's actually 24 exposure elements. This is a really difficult problem. How do we really try to understand the implications? Well, say, for example, maybe I don't want contours. I see a bunch of surface area. I say, well, what if I just turn those off? Well, you can do that. You certainly can, and there's going to be a little bit of an implication, and it's really going to come down to the quality of the surface and really the material fidelity. So in this view, you can see there are two images where we're actually looking at melt pools. So this is not really super magnified or anything like that. So we're not analyzing grain structure, but in this view, you're actually able to see the generated melt pool. And you can see, especially if you blow up the screen and zoom in, the hatch has much larger melt pools relative to these very skinny, almost striped-looking contours that are on the edge of the parts. And similarly, if you look at the other chart on the right, the hatch, you can actually see where it's changing orientation of the hatch, so you get almost like a nice stitching type type quality. But you can still see that there are contour passes that help to smooth the edges of these parts down. So ultimately, using contours and using all 24 exposure elements that you might have available to you is really the way to dial in the process and get really, really high quality parts directly off the print. If you wanted to make the trade and eliminate those, you can certainly do so, but you should expect that if you start eliminating exposure elements, you're just going to see a reduction in material capability. So in most of the time, that's going to manifest itself in terms of fatigue, or in some cases it might be creep. Anything where you have a surface kind of induced phenomenon. In this case, you're going to propagate a crack off of a surface. That's what you'd be working with. So kind of the summary here is that complexity could be less expensive. And it normally is when you're talking about things like a complex forging, casting, machining, something where you're fighting complexity versus a conventional process. But you don't always win with additive just using kind of everything, stock parameters, stock machine configurations, that kind of thing. In some cases, you can really push the business case over the edge by utilizing a combination of reduced material requirements, changing your material parameters so that you can create something that's a little bit more productive if your industry allows for it. In some cases, the quality is the part that really, really matters, in which case you just have to take into consideration that there is complexity that's going to be inherently in the part, which means that you're just going to have an inherently slower process. So what we're really looking at here is that as complexity increases, if you look at your minimum entitlement, might be like a bulk. It'll be referred to as a bulk, but just a hatch assignment. It'll have a nice, fairly linear trend. You're going to see a little bit of variation there based on aspect ratio of the cross-section. But ultimately, you have a full parameter set that consists of contours, edge passes, upskins, downskins. The list is 24 items long. As you increase complexity, you have longer build times. That will always result in a higher part cost when all else is held constant. So we'll move on to another question. Allison, please take it away.
Thanks, Nick. All right, so great examples on complexity and understanding whether or not complexity is free, and what that phrase or that myth means. The next phrase or myth we're going to look at is my machine prints at the quoted entitlement. True or false? My machine prints at the quoted entitlement rate. So let's take a look at the result for this poll question. So a little bit different than the previous here. 14% said true and 86% said false. So once again, Nick, I'll ask you for your thoughts on the results of the poll question.
Yeah. Once again, I think we might have a lot of experienced users that have probably run into this problem themselves already. But the quoted entitlement rate in a lot of cases can be something as kind of abstract as simply what my scanners are capable of producing. In which case you're going to see numbers that appear to be super large, and if you're comparing the wrong thing across different machine vendors, different machine technologies, it can be a little bit misleading. And so I think that's one of the major things here is that people who understand that this is false, if you've experienced the machine, you've set them up in your factory, you've run them, you've probably already hit this. So reality number 2, entitlement is not the same as production. And that's a sensible conclusion, but let's dig into kind of why, what's really driving that. So you'll often hear a metric. This is in a lot of marketing literature across the board, and it's also a metric that has been used substantially for probably the last decade in additive. But we're talking about a volumetric deposition rate, CCs per hour. So you'll have a lot of people say, well, my machine prints up to 60 CCs per hour. Well, if we really think about it, it can never actually really print to these entitlement speeds. So if we go back to our definition on OEE and we start to analyze what are the contributing factors, or how should I evaluate a supposed maximum machine productivity speed, and how do I tie that back to what my ultimate, performance metric is, the overall equipment effectiveness. When we're talking about availability, we're talking about things like how many shifts do I actually run in my factory, how long does it take to empty the machine out, take the printed parts out, reload with powder, and restart the machine. Or how long, is my machine going to be down for different types of maintenance issues. So that all kind of speaks to the quality of the machine itself, but it also speaks to a lot of economic choices that you have to make as as a business making the evaluation. You're factoring in your facility overhead rates. You're factoring in maybe you only have one shift operational because you just don't have the people available to actually run the machines. If we're talking about performance, this is kind of the big one. This is the one that's going to lead to a lot of the confusion and frustration about adoption of additive. So we're talking about what material parameter is actually being used. So as we kind of discussed before, there's all these elements that kind of create that set of instructions the machine is reading. So which one are you actually going to use? And that makes a huge difference in how productive the machine can actually be. And then the other big one is how complex is my input geometry? If you're printing a batch of very small, very non-complex parts, they're likely going to be much cheaper than building one single, very large, very complex part. And the way that those scale is really subject to a lot of analysis. And that's something that we could potentially talk about in a future session. But quality is kind of the other major piece of this. How many builds actually completed? So it's, how many bad parts did I actually create? And then, in terms of the number of available, parts that I have actually printed, how many of them meet my geometric, feature, compliance to my tolerances? Does it meet my engineering functions? So all of these things really do contribute to the overarching picture of let's derate that maximum capability and turn it into a more sensible number. So I have an example here. There's 16 parts. They're just, a random arbitrary part. So 16 parts built in 316 stainless steel. We've only enabled just the hatch elements. So as you saw on the previous slide on that graph, we're just writing that hatch line. And I have two lasers working all the time. So this would be considered, probably a pretty highly productive scenario. I have the simplest exposure, the simplest parameter set that I could possibly have. And I have both of my lasers working at the same time. So with deposition rate, you can kind of see here, 62 CCs per hour. So that's a pretty fast rate. So, what happens when I start to change the scenario around? Well, if I'm looking at hatch only, you can kind of see the picture looks actually a little bit blurry. So this is actually not out of focus. This is just the way the surface looks. It doesn't have very, well-defined lines. It looks blurry. It's very highly refractive of the surface, so you don't really see any of the shine that you would expect with a typical metal. But on the right-hand side, if I have all of my exposure elements there, you can actually see very, very, crisp lines, good detail on the edges. You can also see that the surface looks a little bit more lustrous. So you already can see the benefit of having all those extra exposure elements. So what happens now whenever I turn all of those exposure elements on? Well, I get the better part that you saw on the right, but I see a pretty substantial change in my build time and my deposition rate. Before it was 62 CCs per hour, but now it's only 14. And so that's kind of the consequence of, if I have the part quality requirements that force me to use all of those extra exposures, and I have a part of, moderate complexity, it can have a pretty substantial impact on my total throughput, and that's something that we factor into our ultimate business case. But if I further change the story here, now I'm only going to use one laser at a time. Let's say that for an equivalent set of inputs, I'm unable to use stitching. I can only have one laser firing at a time. Maybe in a real-world scenario, a laser goes down, but you still have to be productive until you can get in and repair that. We've taken the laser out of the equation, and now we're down to a mere 7.9 CCs per hour. So there's a lot of things that really contribute to ultimately what your productivity is going to be. So we'll get into all of those contributions after the next question.
Thanks, Nick. Real quick, we've had a couple people ask for a description of entitlement rate. Could you just briefly define what you mean by entitlement rate?
Yeah. So sometimes you'll see somebody quoting that the machine is capable up to a max speed. So that is usually considered what is my optics speed, or what is the rate at which I can, essentially expose a stripe across the build chamber. Sometimes you'll see those quoted up to certain numbers, like maybe it might say 2,000 meters per second, or it might say 2 meters per second, 2,000 millimeters per second. Those are often listed as millimeters per second. They are also commonly referred in the deposition rate, the CCs per hour. You'll see those quoted a lot of times at like 200 to 300 CCs per hour for like a DMLM process. The deposition rate increases depending on what technology you select. So an electron beam might be quoted as high as 400. If you get into any type of binder jetting, that can be quoted as high as 1,000. So those are some of the common numbers that we see.
Great. Thank you. So I think that's a good lead in then to our next poll question, which is CC per hour is a good metric, true or false? Once again, CC per hour is a good metric, true or false? Curious to see what you guys think. So let's take a look at the results. Oh, wow. So on my end, I show 100% of the audience selected false. Nick, what are your thoughts on this?
That is actually encouraging. You guys all, I think, understand the issue with CCs per hour, which is fantastic. It can be useful in some contexts. Overall, when it comes to establishing a business model, it really isn't that useful. And the reason why is actually coming up. So CCs per hour, or any type of volume metric, or just associate it to mass somehow. So you can take weight, you can take volume, looking at it just from a mass perspective. That metric is really good for specific deposition rates, but the key word there is specific. So CCs per hour is directly associated to kind of the three primary influences of additive manufacturing, and that's the input geometry, the material, and the machine. So everybody here, I think, understands CCs per hour is kind of a tricky one, because just because I have a quoted CCs per hour rate doesn't mean that the machine operates at that, across the board. And so it makes it really hard to use that as a metric to evaluate a bunch of different parts in a given machine. It makes it really hard to evaluate even the same part in the same geometry if you have different materials that you're experimenting with. So because it depends on all of those things, this number changes constantly, and it is really difficult to use in practice. So one of the things to kind of think about here in terms of how do we want to set the stage for evaluating what are better metrics, because CCs per hour doesn't really work, and we all know that. But if you think about it, it's kind of like having a foundry in a box. There's a lot of processing that happens in the box, and mostly in a kind of mechanical digital format that really replicates and replaces a lot of the activities that happen in a typical foundry. So, for example, in a foundry, you have all the melting of the material. I've got to transport it from an oven over to the area where I'm actually doing my pour. I have to have the tooling already created in place. Not to mention if I have multiple different types of castings, forgings, et cetera, extrusion happening in my facility, I've got really a hard job of trying to discern how much of that overhead rate is associated to the machine activity, to the process activity, ultimately how much of that is just wasted cost. So if you really think everything is happening in the box, You have an operator who, has to actually physically interact with the parts to load the powder, take the parts out, reload the powder. In some cases, in a fully automized system, you don't even have that person making contact with the powder all the time. So everything's happening in the box, but what's nice about that is that all of the activity of the machine is happening in a controlled process, a documented process. But I also have, all of the source of the laser power, the inert gas, all the other stuff that's going into that is happening in a way that can be measured directly in the box as well. So this is a kind of a nice way to set the stage for how might I look at the metrics appropriately. So just to really bring home the point why CCs per hour is a little bit difficult to use, we have 3 parts, and across these 3 parts we actually have various levels of geometric complexity, and so they're all fairly similar. So it's not a huge range, but you can see just from minor changes in complexity. If I build the same part in cobalt chrome, so I'm going to read left to right, I have CCs per hour that's varying pretty substantially. So in this case, about 20% change. Just based on the geometry input, I've left everything else constant. If I go down each column and say I've left the geometry constant and the machine constant, if I change my material, now my CCs per hour is all over the place. It's about 60% change. So that's kind of an interesting consequence, and it really does illustrate why CCs per hour is such a difficult thing to use. But it's also kind of indicative of the 3 major variables. The geometry input changes, the material changes, and whenever we see a machine change, I ran these same numbers with 2 lasers instead of just 1, and that obviously led to a substantial increase in my productivity as well. So you can see here input geometry and complexity. This is kind of a generic case. So I said the previous slide, those examples is about a 20% change based on geometry. We've seen about a 3,000% change depending on the level of complexity and the input geometry that you put in. So this is taking a really complex, maybe think of it as like a highly latticed structural component, maybe something like a heat exchanger that requires high surface area by definition. You can see these massive, massive implications about the input geometry, the complexity, and the effect that it has on my total price at the final tally. But you can also see material selection is going to make a huge difference, and that's a sensible thing to think through. If I change my material, the material behaves differently. Steel and aluminum behaves very differently. You have one that wants to melt pretty nicely, very easy to weld. You have another one that wants to just immediately suck heat out. It immediately wants to reflect the laser input. So when you start talking about the actual material considerations, those are things that are real-world physics that you can't really, get around. You can make minor improvements and tweaks. You can have some materials close to parity. So, for example, maybe like a cobalt chrome or nickel alloy. These things are fairly similar in behavior, at least on the AN level. And so their build times are relatively similar. But lastly, the machine architecture, we have 50% here because we have at least, if you double your lasers, that's one way of doing it. If you radically redesign your recoding system, that's one direct way of doing it. But the more lasers you add with the current state of the art, the more entitlement you get. And it really does get up to a certain point. So there's a rate of diminishing returns there. The level of investment of adding additional lasers eventually kind of becomes too complex for the benefits that's received. So you'll commonly see a lot of processes right now. They have, probably up to 4 lasers. There's a few systems that do more than that. But you're not going to see a lot of difference there in the short term because there's so much more to gain in terms of education on the input geometry, how to design for additive, and then ultimately the material selection. So I'll walk you through real quick a few other examples. So cost per volume. So this can be that dollars per cc type thing. But it's a if we're talking dollars per cc, it's a good way of establishing how much work is actually being done on the input material. Whereas something like a cost per time, it can be pretty useful as well. But the difference there is that I'm almost looking at it from a premium. how much of the additional downtime yield, I'm including all of those other aspects into this. It can be super useful, but maybe not necessarily, the total winner. And I hope this is not a shock to anybody, but the best metric that we found to use truly is just the dollars per part. And the reason why is because that is the kind of the final summary of all of the inputs to the process, and it's independent of the, direct, it's independent directly of the input geometry and materials. So clearly it'll change as those things change, but it's not as intimately tied to it as like a CCs per hour, a deposition rate might be. So we kind of put all of this together, the combination of all the different changes that you can make and how it has a direct impact on your part cost. If I look at the three primary cost drivers, I have an example here, and you can kind of see the breakdown that we're going to discuss today. So there's a lot of different ways to do this, and we can certainly talk about all the other ones at another point. But we're going to look at the materials that's being input, the labor assigned to it, the machine itself, the cost of the machine itself, the consumables. This would include all of your electricity, your inert gas, your recoater blades, your build platforms. So we'll include all of those things. Ultimately, we're going to include heat treating because that is part of the ultimate, final requirement for this part, for this example. But we'll also include maintenance, and if there's any other post-processing costs. In this case, there was a surface finishing, per item that was about $22. So on the left, we have the same chart that you just saw. That's a relatively complex geometry. But I went in, simplified the geometry pretty substantially, cut the surface area down in about half. We went through the analysis. The part still functioned the way that it was supposed to, but we just took some of the additional complexity out of the part. And you can see here what's highlighted, there is an immediate impact to the machine contribution to that final part cost. There's also a change in the maintenance and consumables, which is kind of a sensible thing. I've created something that has a lower build time, more productive process because I've simplified the geometry, and I had a direct impact on how much of that machine is associated to that build and the direct things that are a part of the process, the consumables and maintenance. So if I take that simplified geometry, which was originally in 316L on the left, and convert that over to F357, you can see another massive implication here. The machine price, the machine cost associated went down substantially. But also the material cost went down a lot. Well, F357 is much cheaper than 316L. But we also see that, consumables actually went up a little bit. There's a difference in price of the input, requirements to change in the filters, scheduled maintenance, that type of thing. And you can see the direct impact on maintenance. But what's interesting here is that, I changed my material to a much faster, much more productive material. So if you think back to CCs per hour, it's probably a higher CCs per hour. But it's actually, now being dominated by the heat treat costs. And if we take that one step further, previously I was building all of that on one laser. So now if I change the scenario to a dual laser, again, massive implications to the machine, consumables, and maintenance. I'm far dominated now by the other, the other processes that are being accounted. So if we just look at, quickly what the metrics, how they actually kind of stack up, you can see CCs per hour actually increased across the entire process. So we changed to a more productive material. We also changed to a more productive machine architecture. We reduced the complexity. But we see this kind of shift happening where whenever I changed to F357, my dollars per CC actually increased, which is kind of the opposite direction that you want to go. Ultimately, throughout this entire thing, I created a more productive process, but I actually had an increase in dollars per hour. And that inverse relationship of dollars per hour is going to hold true as long as everything else remains constant. And so that's an interesting implication because that's essentially saying that the higher the premium I'm paying for every hour of productivity that I'm gaining, I'm essentially spending more money on the process if I'm measuring it relative to time. So there's a little bit of that time premium that goes on this. The obvious implication there is you can chase that back down if you start talking about different machine architectures, getting into, probably more exotic state-of-the-art development type work. But if we look at dollars per part, it actually went down when I simplified the geometry pretty substantially. It went right back up when I changed my material because my material required a different heat treat. And then lastly, the final, reduction using 2 lasers instead of 1 positively, impacts my business case. So it's kind of an interesting study because what it's showing is that a more productive process, CCs per hour, is always getting bigger and better, but it really didn't have a direct correlation to what my final dollars per part is. And so if you examine the results here, you can kind of see interestingly, CCs per hour and dollars per hour are going to follow somewhat the same trend. And again, that's really associated to more productive process. I'm spreading less of that, full total all-in additive cost across fewer hours. And so I end up paying more money per hour. And if I look at the trends really on the kind of dollars per CC or dollars per part basis, they start to actually follow a little bit more in line. So you'll hear a lot of machine OEMs, I think, now moving forward, have been leveraging the dollars per CC as one of their standard metrics because it aligns better trend-wise with a dollars per part basis. So these are really kind of the 4 primary objectives that we're really utilizing on a daily basis. There is still a place for CCs per hour, and it's really when you're just talking about pure machine throughput. It's not going to be useful otherwise. You can't say that my machine produces at 60 cc's per hour. It can, under the right circumstances. It almost, never does. It's going to be very specific to the part, the material, the machine architecture. Dollars per cc, again, is really about evaluating the work that's being done by a given material on a given machine. And the higher that is, the more that I'm paying to convert that powder into a usable part. Dollars per hour is that premium. The higher that gets, the more we're talking about a more productive process. So in some sense, that can be an indicator of a good thing. And then lastly, dollars per part, the best way to evaluate competitiveness of not just additive processes, but you can compare back to conventional processes as well. The key there is just to be sure that all of the additional post-processing is all together. So, to really conclude the entire presentation today, don't make something complex just because you can. Additive technology still has a cost of complexity. It's just usually a lot lower, a lot easier to wrap your head around rather than the, maybe months of lead time and tooling and all that other stuff that might be associated to a conventional process. So it's cheaper to go additive and go complex, but there is a cost. Your machine productivity is really the cornerstone to the entire business case. And so the more you understand how the machine's actually behaving, we talked about exposure elements and we talked about the kind of construct of the parameter set or the instructions the machine's using. That has a huge implication on what your final part cost is going to be. And then lastly, measuring machine productivity is tricky. But, thankfully nobody here was fooled. You all voted in the right direction. But it can be really tricky, and in some cases you really do have to leverage multiple metrics to really tell the economic benefit. And whenever you're presenting your business case out to investors, to executive leadership, you want to be sure to kind of include as many different metrics that really point to the right behaviors, the right, measuring the right thing is always paramount. So I'll pass it off to Allison.
Thanks, Nick. So we have just a couple minutes left. And so we'll go straight to the Q&A. We've got a ton of great questions today, as usual. So I'll jump right in. First question, how do the mechanical properties differ between hatch-only and full parameter parts? Is there a large variation?
Yeah, this is a great question. So mostly, generically speaking, you don't see a large variance when it comes to physical properties. So, your densities, your elongation, yield strength, et cetera, a lot of those physical properties will remain fairly constant. And so if those are the ones that you're using to evaluate, whether or not it makes sense for your process, those are less impacted. And so you may have a lot more flexibility to, maybe optimize your parameter set in order to just meet those requirements. Where we do see the biggest impact to, changing to just a hatch-only type parameter set is going to be on any fatigue, low cycle and high cycle fatigue are going to be impacted. You're also going to see a difference in, maybe creep performance. Again, crack propagation is really the key to understanding that phenomenon. So the impact there can be, sometimes quite large. It really depends on the material. But that's the type of thing, we can evaluate, via AdWorks or some of our other services. But generally speaking, physical properties aren't impacted nearly as much as fatigue.
Thanks, Nick. Okay, the next question that we have, obviously today we talked about a couple different metrics throughout the presentation, but are there any other useful metrics that you'd like to mention here?
Oh, yeah. So there are other great ones, and it depends on the objective that you're working towards. So I would say the two kind of primary ones are your total lead time. That one is where Additive really does shine, but it's very specific to the actual, the business case and whether or not that's competitive. So we'll typically do a summary of not just the build time, but we'll include every single step in the process, handling time. We'll go as granular as to say there's the cost associated to putting the part into its packaging, putting the shipping label on, and shipping it out. So we go super into the weeds there, and then we'll back out and say, okay, now that I've got all of my sourced out, my outsourced post-processing, thermal heat treats, machining, et cetera, that gives me my ultimate picture of kind of conception, CAD model stage to final delivered product. Those times are usually drastically lower than conventional manufacturing. So that's one that we use a lot. The other one is actually NPI cycle time. So one of the other major advantages of Additive is the fact that you have the flexibility and the fact that there's no input requirement other than a CAD model. I can create a CAD model, demonstrate a part capability either in a subset of the part or the actual full part, demonstrate that via testing, and I can essentially use a fast work style design process. And that's something that is a lot harder to do with conventional manufacturing just because of the long lead times. You may order a tooling, it may take 3 months, before you receive that, and then you can make, only what the tooling, instructions are. Whereas with Additive, I can quickly reevaluate. So the amount of time it takes me to introduce a new product is substantially decreased. And that is like the number one reason why a lot of companies are investing in Additive. That speed to market is huge. And a reduction of NPI is also a reduction of the fixed non-recurring expenses that you have at the very beginning of the process.
Great. Thanks, Nick. I mean, you've got some candid experience there to share, so thanks for a great answer. So this brings us to the end of our time together. And as we wrap up, I would like to again say thank you for joining us. A couple key takeaways from today. Remember, don't add unnecessary complexity just because you can. Machine productivity is the cornerstone to building a good additive business case. And last, measuring machine productivity is tricky, but using multiple corresponding metrics can help you to tell the whole story. Once again, our webinar today will be available on demand if you would like to listen to it again, or perhaps pass it along to a friend or a colleague. And I also encourage you to register for our upcoming webinars. And finally, before you log off, I'll ask that you please complete a short survey that will pop up for you in just a minute and share with us how your experience was today. And let us know any other topics you'd like to hear about in the future. Look forward to seeing you guys next time for our Webinar Wednesday series.